Welcome. So I would like to welcome everyone for this IIsc webinar co-hosted with the Applied Photonics Initiative. And today we have Professor Sushil Kumar who will be giving the webinar. He is an associate professor in the EC department at Lehigh University in Pennsylvania. And he obtained his bachelor's degree from Delhi Engineering College, and then his PhD and postdoctoral work were done at MIT. And since fall of 2010, he has been at Lehigh University, and his research spans quantum cascade lasers and using them for terahertz applications. And more broader interest includes terahertz and mid-infrared applications as well in sensing, imaging, spectroscopy of using high power QCLs. And he's also a recipient of US National Science Foundation Carrier Award in 2014. With that introduction, let me hand over to Sushil for his webinar.
Okay, thank you very much, Dr. Raghunathan, for inviting me, and this is a real pleasure and honor. I really was looking forward to this. Welcome to all the faculty and the research scholars and scientists, and I hope there are some graduate students as well. I work in this relatively narrow area, and that's really long wavelength semiconductor lasers. So by long wavelength, I mean a really long wavelength. So you are going to more than 10 micron wavelengths, so nowhere near visible. And so we are actually near 100 microns, so approaching microwave frequencies. And not many people know of these sources if they don't work in this wavelength range. So it might be an introduction for a lot of you, or for those who know it, it will be kind of an overview of where we are and the current state of the art. It does require a fair bit of prior work and experience to get into this area because these are fairly complicated structures. So that's why we don't have that many people around the world who work on it. But if you have to look at quantum cascade lasers, there is a lot of activity, or reasonably good amount of activity in Europe and Switzerland, Italy, France, not that much in USA, and I don't think that much. I don't know of any active groups who do it in India. So I'll be talking about terahertz quantum cascade lasers. So for abbreviation, and as they are known, I'll call them QCLs here. And in our group, we are trying to increase their power output, which by power I would mean optical power output in the laser itself. These are monochromatic sources, as lasers are, at single frequency, very narrow line width, as opposed to broadband terahertz sources, which most people who work in this area are aware of. So these are laser sources. So at any point, if you would like to just stop me and ask a question, please do so. So I would like to start with just showing the frequency range in the electromagnetic spectrum. It's huge. I noticed a lot of your faculty work in electromagnetics microwave area, and then some are in the photonics area. So it's an appropriate slide to show where I am working in. So when we call terahertz, I'm not in the 5G kind of terahertz nomenclature that people use. Those are more like 100 gigahertz frequency or below, or maybe above and reaching up to 1 terahertz. So that would be somewhere, right here. This is 1 gigahertz right here. So I'm going to 10 gigahertz and then 100 and then 1 terahertz. So as you go to higher frequency from left to right and shorter wavelengths, so this is kind of the frequency range from 1 terahertz or 1000 gigahertz to about 10 terahertz. It's kind of been always a underdeveloped or a black region in the spectrum, because there's no good way to generate this light, no good way to detect this light. Detection has existed much longer, but generation is still a challenge. And so where our sources, these quantum cascade lasers, work best is around 2 to 4 terahertz range, which will be a wavelength of about 100 micron and whereabouts. So just to give you an idea, communication wavelength is 1.5 micron. So that's a frequency of 200 terahertz. So we are working at, say, 2 to 4 terahertz, or 100 factor lower, and therefore a factor of 100 higher in the wavelength. For those who think in terms of energy of the photon, 1 terahertz is 0.004 eV, or 4 MeV, milli electron volts. So just to give you a kind of a illustration, at lower frequencies, microwaves, we have actually, the way we mostly generate light is using oscillators, electronic circuits, and there's actually physical movement of charges in the wires, and then we have antennas, and that's how we generate. At the higher wavelength, higher frequencies, which we can call photonics, it's really a quantum mechanical phenomena purely, and the electrons radiate because they make these quantum mechanical transitions from conduction band, which is, let's say, shown up here, to valence band. So here the photon energy is mainly determined by the band gap of the material you choose, and you can adjust this a little bit by making these quantum wells. So somewhere here it's like is challenging. It's difficult for the electronic circuits to go much above 100 gigahertz, as you most of you are aware of, and for the photonic sources, such small band gaps don't really exist. So what we need to do is we actually make these artificial materials which can somehow achieve very small photon energies. So I mean, typical band gaps are of the order of 1 eV, and we need 1,000 times or 20-30 times smaller. So that's I guess this is what are the applications. If you notice, this is a graph that shows one of the earlier applications, or traditional applications, has been always in astrophysics, in astronomy, remote sensing of outer space, or even Earth's atmosphere. And this picture shows the kind of the black body spectrum at 30 Kelvin, which is the temperature of interstellar clouds. The cosmic background is at 2.7 Kelvin. So if you look at the black body center wavelength, that's around 2 millimeters. So I think that will be 2 millimeter would be around 150 gigahertz microwave range. But interstellar, that's where people are interested in studying star formation, galaxy formation. It centers right around this 2 to 3 terahertz, and all these molecules have these rotational and vibrational modes, and they emit strongly in this wavelength. So there is a lot of terahertz photons in the universe, and they're reaching us, and we want to detect them and understand. And by understanding their line width of the radiation and so forth, we can study what exists in those interstellar clouds. So these are some examples of even now there have been, but these are few years ago or tens of years ago, maybe 10 years ago, some of the instruments that have been sent into space to study terahertz light. And the way this is done is through heterodyne spectroscopy. So for example, if you have a really weak signal in terahertz, let's say 2 terahertz, and really weak signal you want to detect, so what you would do is you would receive that signal and mix it with a local oscillator also in terahertz, let's say around 2 terahertz, and use a nonlinear mechanism to mix them with a mixer, and then you amplify that your signal is converted to microwave in gigahertz or megahertz, and then you can use microwave analysis or detection techniques to analyze that spectrum. So again, for this, receiving this terahertz signal, you know, not only you need a detector, but actually you need a local oscillator, so which is working at 2 terahertz. So even that is difficult. So these instruments actually use local oscillators around 1 or 2 terahertz, and they have been generated through years and years of research, for example, at JPL in NASA, and they are very complicated instruments. And I'll tell you the for example, you may have heard there are Schottky multiplier chains. So you would use a 10 gigahertz source, for example, you keep on multiplying it 10 times maybe, or 50 times, doubling it every time, and then you reach 1 terahertz. And by the time you reach 1 terahertz, the power is really small. But the good thing is that for local oscillator, you don't really need that much power, so you can still do this. So these instruments are carrying those multiplier chains actually. So this has been so it's really difficult to go above 2 terahertz. And that's where a lot of interesting phenomena also exists. Back on Earth, if you want to look at applications, there is applications, pharmaceuticals, security industry. For example, here is this a spectrum of common explosives. So TNT, HMX, PETN. This is from the 300 gigahertz going all the way to 3.9 terahertz. You can see each chemical has its own specific signature, absorption spectrum. And the good thing is terahertz, like microwave, can penetrate some common materials like clothing, packages. Not as good as microwave radiations. It cannot penetrate walls or metal. Well, metal microwave cannot penetrate either, but walls and bigger, thicker packaging. But still, it can penetrate thinner layers like FedEx packages and so forth. So you could do potentially non-invasive spectroscopy and even chemical analysis and detection if you had strong light sources in this frequency range. So that will be one application. So some of the studies which are mostly done in this range, well, before I go on, I want to show you one movie of what kind of modes I'm talking about. So this is a TNT molecule. And this I obtained from one professor, X.C. Zhang. He's a director of University of Rochester. He does research on terahertz. So this kind of shows like a vibrational mode. I think it's around at 2.5 terahertz of a TNT molecule. So these are the kind of modes that are very strong, have very strong absorption features, and you can shine light and the absorption peaks that you see are corresponding to those kind of absorption, rotational or vibrational modes in these big molecules. Bigger molecules like proteins, DNA also have very specific signature at these frequencies. So these experiments that are done with very, very thin powders prepared, because at the end of the day, these are very lossy materials. So and the challenge is here, terahertz is absorbed very heavily in water and any type of liquid. So give you an example, the water absorption loss of water for this kind of frequencies around 3 terahertz, 2 terahertz is about 600 per centimeter. So which I evaluated comes to about 10 dB loss for a 40 micrometer thick channel of water. So you'll have about 90% absorption in just that thin layer of water. And methanol is maybe 2 to 3 times smaller loss, but it's still of the same order. So if you want to do any liquid-based spectroscopy, you need really high power. So this is where we are getting at in our group, and now we are kind of at that level that we can start to do spectroscopy in liquids also potentially. So that's why it's not, even though there have been applications proposed for imaging and biology, most of the applications are at the skin level. So some people have proposed to detect non-invasive skin cancer by shining terahertz light, but not penetrate too deep. Obviously, few tenths of microns would be the maximum if you had a high power source. Another example is this pharmaceutical products, for example. So I'm going to skip some of these, but just to give you an idea where we lie, these are some of the types of radiation sources that exist. And there are these gas lasers. For example, there will be a CO2 laser which emits a 10 micron wavelength, which is mid-infrared, and it would then so that the frequency will be 30 terahertz. It would pump CO, carbon monoxide, for example, and maybe that's how they generate terahertz source light. These are big instruments, take the whole tabletop, and they are available, but only at some specific frequencies, and their power is of the order of milliwatt. And then I'll come back to our QCLs. We can now in QCLs actually we can reach now watt level in pulse mode. So if those of you who know how to operate lasers, you only bias the laser for a specific duty cycle, let's say 5% of the time, and then keep it off. So that's the peak power is 1 watt. If you look at average power, you multiply by the duty cycle. So average power is around 100 milliwatt. That's where we are. But the challenge is they require cryogenic cooling. Well, that's why you don't see them right now in commercially, and anybody is not really selling them. And there are some other challenges still to be met, which we are trying to work on. So nonlinear sources, you mix two other frequencies, try to generate power. So for example, Dr. Raghunathan mentioned QCLs themselves can be used as nonlinear materials. And there are Schottky multiplier chains I mentioned to you. They use these Schottky diodes, and they keep on multiplying a microwave source, and they reach about 2 terahertz. All these sources and some of these broadband sources. So you have a femtosecond laser shining on a photoconductive antenna, and you can generate these broadband signals by rectification. So of the envelope of the pulse. All these sources, the average power is about milliwatt or maybe maximum 10 milliwatt, and that's really and they become very expensive. So that's where we are trying to compete with and try to see that we can. These powers are nearly not enough to be able to do anything. The kind of spectroscopy that I mentioned in the lab, perhaps work has been done, but if you want to do it in a viable manner, that's not. So that's where these QCLs are, but they have their own challenges, which I would like to outline. So I won't probably cover everything. I'll see how much I can do here. So I will just explain how they work first of all, and then where we are working on and how we are increasing their output power. So there's some bit of cavity design for lasers that is being discussed in this presentation. Some of you can relate to, some of you who work with metamaterials or plasmonic modes, metals tying with the optical modes, or even in microwave antennas can hopefully relate to it, because we are kind of in the spot between microwave radiation and photonic radiation. We are using metallic cavities. The cavities that are used for these QCLs are like microstrip transmission lines. So there's some association that can be made for those who are studying or use microstrip lines. So as I mentioned to you, the top figure here on your screen is an illustration of interband light source. From conduction band to valence band, you can make quantum wells and you can adjust these levels. This is an electron level. This is a whole level or subband, and then electrons recombine with holes to generate photons. And these are how we generate near infrared or visible light. So the frequency set by the band gap. In QCLs, we do not use holes. So these are n-dope devices, no p-doping needed, no holes are needed. And you can, by making this quantum well, for example, this is gallium arsenide, aluminum gallium arsenide, adjusting the thickness of the well, you can change the separation between these levels. And you can, if you can somehow have electrons occupy a higher energy subband, so achieve a population inversion, and that's how you get optical gain. And then when you put that in a cavity, you can get a laser. So that's the concept. It's easier said than done, obviously. So it's a very complicated structure. In fact, modeling of quantum transport in these devices is still not very accurate. A lot of groups work on it, but still not there. It cannot really model very well. So the key thing is these are artificial. The frequency is in our hands. We make the width of the quantum well the thickness that we want, and we can really adjust the frequency that we want here. So you can call it artificial atoms, if you will, or semiconductor superlattices. So this is like an perfect example of band gap engineering. So this is how a QCL would typically be. For example, you will have maybe 100, 200, 300 micron or 600 micron thick gallium arsenide substrate. Most common material for terahertz QCLs is gas L-gas. Most common material for mid-infrared QCLs is in-gas indium aluminum arsenide. Just to give you an idea, I don't have a picture of this. QCLs were first invented at Bell Labs in 1994. Those were mid-infrared QCLs, so those were around a wavelength of, I believe, 4 to 5 micron. So they work in this spot of 4 to 10 micron wavelength of emission of light, and then terahertz, which is around 150 micron to 50 micron. So in between, they don't work because of absorption in the semiconductor, polar semiconductors, that you cannot generate that light. So these are mid-infrared, 4 micron to 10 micron, and then terahertz, which we are 150 micron, 50 microns, so it's frequency of around 2 to 4 terahertz. That's where I work in this. But the concept of their operation is pretty similar. Even though the valence band is shown here, it does not take part in the transport. There is no holes because there is no p doping. And then you would grow these layers in a repeated fashion, one on the top of each other. So lattice matching is crucial. So these are some of the most challenging structures to grow using molecular beam epitaxy. That's the mechanism that's used. So let me just tell you, so for our typical terahertz QCL, it's about more than 1,000 layers have to be grown. And there is this module like of maybe 5 to 6 layers or maybe 7 layers, and that's called a period, and that's repeated about 200 times. So there is a repeat of a periodic structure that's repeated. And this structure is designed through some calculations. If you perform, basically we use 1D Schrodinger solver to calculate the subbands and the electron wave functions in this. So it's not that complicated. Transport cannot be done, but we can do some basic estimation based on experience and also some basic calculations with the Schrodinger Poisson solver. Typical layer thickness is from few nanometers to about 15 to 20 nanometers each layer, each well and the barrier. So these are nanometer layer scale thickness devices, and this structure is grown for almost a whole day to achieve a thickness of 10 micron in the end. So I am not a grower. I do not know growth very well. We design these structures. So by design, I mean we solve and we calculate how thick the layers should be, and we collaborate with somebody here in Sandia National Labs. That person has been great for us, Dr. John Reno, and or you can have these commercially grown. Very expensive. We asked somebody how much they would charge, so they would probably charge $5,000 for growing one QCL wafer for us. But we luckily, the way we are able to do this, we have this collaboration going with Sandia Labs. So they grow these structures for us. Now, how they work. So this is a really simple structure. The actual structure is a little complicated. This is gas L-gas. So the barriers will be aluminum gallium arsenide. The wells would be gallium arsenide. And these dashed lines correspond, they are showing subbands, electron subbands once you calculate. And in general, the electrons will be occupying the lowest subband. So by times n, I mean in this picture that you have n times. This two-well structure, two-well, two-barrier structure is repeated n times. And that n can be about 100, 200. And the way it works is at the ends, you apply a DC voltage. So even a battery, a typical voltages that we apply is 10 volts across the 10 micron thickness. So then you establish an electric field, a DC electric field across the structure, which bends the band diagram because you're applying a potential with distance. And that bending of the band diagram moves up these energies. So now you can have these energy alignments. And by resonant tunneling, when the energy, this lowest state in one of the wells aligns with a higher state in the adjacent well, electrons can tunnel through. So there's tunneling, quantum tunneling, or resonant tunneling as we call is the key to how these structures operate. So let me show you a cartoon movie from a professor called Gottfried Strasser, which I have worked with, and they have I have his permission to use the movie that he generated. So it's kind of nice. I hope you can see this. This is a blob of electron wave packet, or you can think of electrons moving through these structures, and they are undergoing various scattering mechanisms in the semiconductor superlattice, but in one of the wells they can emit a photon, and that depends on several things, so I won't go into there, but it's like a repeat structure. So it's a cascade. So it's a cascade of electrons. Each electron goes through these 200 different repeat periods, and every time as it cascades through the superlattice, as it travels, it generates 200 photons. So it's really a unique way that it works. I want to show you also this is something I generated for a very simple structure. So you can see in this image, gradually the electric field across this structure is being increased. And these wiggly lines are basically probability density of electrons in each of these three subbands. So this two-well structure is repeated. Most electrons occupy this level, but as you keep on increasing the voltage, at some point, some levels align with the levels in the adjacent well, and here, for example, here the blue level is aligning with 2. This is not actually good. You need to align with 3. Then you will, they are overlapping. There is a radiative overlap. So for those who have, who are aware of how semiconductor lasers work, you need an overlap between the wave functions of electrons and holes. And when we keep on biasing higher and higher up, we start to inject electrons through tunneling into this higher level, and that's where we get gain in the system. So now our system or our material has optical gain. If we shine terahertz light through it, it will get actually amplified. And when we put this thing in a cavity, then it just suddenly starts to emit light like a laser. So it's as a laser. So I'm also showing for the same image that I showed, this is how we would do it. So on the horizontal axis, you see voltage being applied to that structure. And the red region is where we start to see lasing action. And that's, if you notice, these bars show how many electrons are in those 3 levels. And this, as electrons, there are always a lot of electrons in the lowermost level, but once the electrons start occupying the higher level through resonant tunneling, you get population inversion, and then lasing starts. So this is an IV curve of this device you will typically see. This is the voltage, this is the current. So if you were to measure just current voltage curve of a QCL, that's how it kind of looks like. There's no light data shown here. It's just, this is kind of a simulation. This is not an actual curve. I'll show you the actual curve a little later. So I have another kind of animation showing how resonant tunneling works. It's basically the electron wave packet oscillates back and forth, but as it moves from this 1' state to 2, what happens is in state 2, it quickly falls back into level 1 of the next stage. So it's tunneling back and forth, and then it's kind of getting extracted. So that's how electrons move in this QCL structure. The scattering mechanisms that allow this to happen are electron phonon scattering and electron impurity scattering. And so there are a lot of semiconductor solid state physics that's involved in understanding, which we don't have. We do some basic calculations for electron phonon scattering, but you need a much more detailed analysis of how these work. So nevertheless, that's how we design, and I think that's all I will say. Mid-infrared QCLs in this picture, this is from 2010, are already commercial. You can actually buy them. They do cost a lot of money, maybe $5,000 for a good laser you can buy, but people buy them to do mid-infrared spectroscopy in their labs nowadays. But terahertz QCLs are not commercial yet. I'll skip some of this. Some of this work we do in actually trying to improve their temperature performance. So this figure that shows here is for terahertz QCLs. One thing to note here, they do not work at room temperature. So that's one of the challenge. As temperature becomes hotter, it's very difficult to have this population inversion. So electrons do not stay here, they scatter back and fall back into the lower level. So you have to cool them down. And the best we have today is this result. They do work up to almost 250 Kelvin, which is about minus 225 degrees C or something. But that does not mean that you can actually have cool them with some cooler and have them working. This kind of figure, I'll show you some more of this kind of figures. This is current and this is light. Okay, so that's how a laser typically is characterized. These are called Li curves, light versus current. So when you keep on increasing the current through this device, it starts to laze, it starts to emit light. So this light is laser light, and the power keeps on increasing, and that's the maximum it can reach, and then suddenly drops because something happens and does not work anymore. So these are temperatures. So these are the curves measured at different temperatures. So what you can see, they have the highest power output, about 100 milliwatt at 10 Kelvin, and as you keep on increasing temperature, power drops. Now this is a Fabry-Perot laser. It has a horrible beam. I'll show you a little later. So this is by no means ideal. Fabry-Perot lasers without good beam, without anything, any external effects added to it to make it a proper laser, it works at 250 Kelvin at the maximum. But to get sufficient power out, you still have to cool them around 80 Kelvin or below 100 Kelvin. So that's where we are working at. And I think that's where it will be in the end. Any application that will use these lasers will have to be considering the fact that they will be working around below 100 Kelvin temperature. So you'll have to cool them with liquid nitrogen around 78, 80 Kelvin or so. So the way we do it, so I'll skip this slide. The way we do in our lab, we use this Stirling cooler. So this is the main component of this is this Stirling cycle cooler, which is of few like a shoebox size. And then we have built a vacuum chamber. So we apply a vacuum pump here and evacuate this chamber. Our laser is sitting inside this chamber, which we machine ourselves or have it machine designed. This is an optical window through which the laser light comes out. It's made of typically polyethylene because glass is not good. It will absorb terahertz light. So not many materials that are transparent to visible light exist. So we have to use polyethylene, which is a fairly transparent material for terahertz. And that's how we characterize lasers. So they're sitting in the vacuum chamber. They're being cooled on this plate at around 80 Kelvin. And this is the good thing is this does not require liquid nitrogen or liquid helium. We plug this in, it takes about an hour to cool down. So potentially if somebody wants to take it on a car or a truck in the field with a diesel generator or electric generator, you can do this. You need a vacuum pump to evacuate, and you need electricity power supply for this instrument. It does make some noise, but that's where we are at. If we can, some applications can take this kind of a operational requirement, and then these will be the best. The thing is that these lasers are by far the most powerful sources of terahertz radiation, above 2 terahertz. So I'm not talking about the 5G level at 100 gigahertz, but there's nothing close to the kind of power that we can have. So if there was to be something which will eventually get commercialized, I think these are the candidates which are probably much ahead of the game. So here's a picture of how our laser in that chamber sits. This is a copper block that gets cooled to that temperature. Obviously, we have to then mount this laser mount. This is again a copper chip, so it's the size of a coin. The actual laser chip is this. It's about 1 millimeter times 2-3 millimeters. And this chip, if you zoom in on this, these are the laser cavities. So each of them is an individual laser that can potentially emit up to a watt of power. And these are wire bonds. So we wire bond these, and then we you can see probably some gold wire bonds here and put them in there, and using some coaxial cables, then we bias this device. So that's how we electrically bias in the vacuum. So that adds some challenges because of cryogenic instrumentation of how these are operated. So it requires culmination of several things. You have to be able to design these. These are made in the clean room in our university. We give them the layer thicknesses, they grow it, our collaborator, and they send us back the wafer, and then we have to fabricate. Now, fabrication of these lasers itself in the clean room is a long process, few weeks to a month. It requires about, for those who fabricate devices in the clean room, it's about a 4-mask process, and not trivial by any means. So it's almost as complicated as making a CMOS transistor. So maybe I will just show you a picture, but not go through the fabrication process. So I want to move to the cavities. So what kind of cavities we use and why. Conventionally, if you take any laser, infrared diode lasers, like the lasers in your laser pointer, or any other type of lasers, they use dielectric waveguides. So you'll have multiple, as we study in our normal courses, we have dielectrics of different indices and in a layered structure, and that can guide light. Now, that would be unfeasible at these wavelengths. So it's doable at infrared wavelengths, visible wavelengths, but at 3 terahertz, for example, the wavelength in air is 100 micron. If we were to use gallium arsenide, about 30 micron wavelength inside gallium arsenide. So the dielectric layer thicknesses has to be of the order of wavelength, or half a wavelength, quarter wavelength. So that kind of thickness, you have to, most of these waveguides are usually made by growing with some sort of growth technology, or some sort of deposition, and that's not feasible. So dielectric waveguiding is not feasible. So what comes to rescue is, well, microwave kind of waveguides, which just use metal, right? So those are just double metal layer is a parallel plate waveguide which can guide light at very long wavelengths. So we very well know that we can guide, let's say, 100 gigahertz light with a transmission line. 100 gigahertz is what wavelength is about, maybe 3 millimeters or 0.3 millimeters. 100 gigahertz would be 3 millimeters, and we can use microstrip transmission line, which is much smaller than 3 millimeters, and it can very well guide that light. So that's how we use. And the reason that works is because metal layers allow propagation of surface-plasmons. So these are the modes that are kind of hanging on to the metal dielectric interface and decaying exponentially on either side. And there you can have sub-wavelength confinement. So that's exactly what we do here. In fact, it looks very much like a microstrip transmission line. The only difference is it's making these are very challenging. So this is how our final laser structure will look like, or does look like. It has metal on the top, a metal plane on the bottom, and this QCL superlattice structure is sandwiched between these two metal layers. And this sandwich has about 1,500 layers which have been grown by MBE, about 10 micrometer thick. And so this is 10 micrometer thick. The wavelength inside, that is the propagating inside back and forth, is, let's say, inside gallium arsenide is 30 microns. So you can see this can very well, there is no cutoff. You can keep it thinner, it still works, and it can confine terahertz light. The reason it works okay is because metal is not very lossy still at terahertz in terms of optical loss. Obviously, it's much less lossy in microwave at microwave frequencies, and terahertz is also not very lossy. And you keep going higher and higher in frequency or shorter and shorter in wavelength, when you reach near infrared, it becomes quite lossy. So that's why you don't see. A lot of people are doing research on plasmonics at near infrared or visible, but those, as everyone knows who works in that area, metal is very lossy. So typical loss for metal in our wavelength is about 1 to 2 or maybe 5 inverse centimeters, which is about 10 to 20 dB per centimeter of travel of light. So probably around 10 dB or even maybe less per centimeter. So that's not too bad because our cavities are only 1 millimeter long. So making of this is another aspect. These layers are grown on a semiconductor substrate. So we need to somehow get rid of the substrate and do some sort of, the way it's done is you flip chip bond, you deposit metal on top of the structure and flip chip bond it. So there is wafer bonding involved and substrate removal, and it's a fairly challenging process. That has been developed over time, not in our group when I was a PhD student and some other groups, and it's been perfected, but still takes a lot of effort. And every time a new student is on the project, it takes them a year or so or more sometimes to get this going. So this is a mode calculated through a finite element solver. How the mode looks like, the red color means just the electric field. It's in the vertical direction. And typical laser, so this will be how what we call a Fabry-Perot laser will look like. For those who know Fabry-Perot cavities, just a rectangular cavity, you cleave them on both sides, you make facets, they become reflecting facets. These are by themselves horrible lasers, not like typical lasers that we see from our laser pointer. So our laser pointer might also have something like this. It may have a VCSEL or a Fabry-Perot laser. It has a fairly nice beam. But if you were to make this terahertz laser, they will have horrible beams. So this is, I'll just show you the beam in a bit. This is what I mentioned to you about fabrication. This was the MB wafer that we received from our, let's say, collaborator, and we grow these layers, and then well, they grow these layers, they send us this wafer, then we deposit metal, we take a dummy wafer and deposit metal on that, and we thermocompression bond it by compressing it in a hot temperature. Once it's done, we get rid of this substrate by chemical etching, and there has to be something called an etch stop layer, and then we deposit metal on top and do some lithography to make this this is how it looks like in an SEM image on a typical laser cavity. So you can't really see the layers, right? This is 1500 layers, gallium arsenide, aluminum, gallium arsenide. The reason you can't see them, well, because that aluminum gallium arsenide is lattice matched, and it's very similar to gallium arsenide. So it's very hard to say unless you do TEM. So this is a typical emission, this image from a Fabry-Perot laser. So anybody who sees this kind of image from a laser, this is how you will, if you were to take a detector and measure the beam of a Terahertz QCL, that's how it will look like. It's really of no use if you think about it. It's not a Gaussian beam by any measure. It can't be really. It's got these ring patterns and very poor. The reason is because this wave aperture that's emitting light is sub-wavelength. So anybody I guess folks in electromagnetics can appreciate if your aperture that's emitting light is much smaller than wavelength, the light will diverge in all directions, diffract. What happens here is the light diverges from this end and this end, and it actually interferes with itself and generates these ring patterns. You need the aperture to be of the size of the wavelength to get a nice beam, and that's not in this case. So that's where a lot of work has been done. So these QCLs I forgot to mention were midIR QCLs were invented in '94. These were invented in Italy for the first time in 2001. So for the first 4, 5 years, 6 years, there was a lot of work done on just making these Fabry-Perot lasers. And since then, the work is mostly done in doing something to these cavities, these simple cavities. Can we make something, can we do something to this cavity to improve their radiation pattern, to improve their power? By themselves, they are very low power devices. You can kind of think of these are high Q cavities. The light does not want to come out because this is a sub-wavelength aperture. The reflection from the facets is very high inside. Light does not want to come out, and whatever comes out is actually very divergent. So basically that's why we are this kind of closed community. We do have these lasers, but we have our own challenges to deal with, which are very unique to these types of lasers. So we're just trying to solve those challenges to finally bring them to a point where we can appreciate. So I am not going to go through, I have to say that at least 30, 40 different types of techniques have been published to make these cavities, to do something to them so that they can emit light in a better beam. Most of these techniques are by doing something on the surface metal layer. Instead of having light coming out of the edge facets, you do something, make some sort of gratings. So you can kind of think like a phased array antenna in microwave. So you leak out the layer, and by having a designated periodicity, you can perhaps, if you know the frequency well, you can have them combine in phase in a certain direction and so forth. So that's the kind of, it's easier, again, easier said than done. Some of our work that we have been doing is this, and I'm going to just directly move to our latest work that we did because we are short on time. So how do we enhance? So this is the work that we published last year, and this is the highest power Terahertz QCL that exists today. The way we do it is we make these second order or Bragg gratings, these slits on the top. If you make these Bragg gratings, if you have, for those who have studied distributed feedback lasers, DFB lasers, that's what it is. Any type of periodicity introduced in a laser cavity can couple light propagating in both directions, so you don't need end facets anymore. And what happens is that periodicity then determines what frequency is coming out of the laser. These type of periodicities can be anything. You etch the semiconductor a little bit, you make some change the layer doping or something else. So there is different kinds of feedback. You can have first order grating, second order grating. What by that it means what Bragg diffraction, what's the periodicity you use to have a feedback. So a typical second order grating, what it would do is it would apply the feedback for the cavity mode to be established. So the first order Bragg diffraction will do the resonant mode for the laser resonance. The second order Bragg diffraction actually comes out on the surface. So it's a 90-degree angle. So if the light is propagating like back and forth in the cavity, along the length of the cavity, the second order Bragg diffraction comes out of the surface. So it becomes a surface emitting laser. Okay, so now we have a much larger area of emission. So this is no longer sub-wavelength, and we can have a much better beam. The problem that happens is the power is still pretty low. So this was the approach that was used perhaps 10, 12, 13 years ago to make these lasers slightly better. What we have now done is we have actually, we came up with an idea here in our group to make these cavities really small. So each are like micro cavities. So each of them can be thought of as mini terahertz laser cavities with slits on top. But now we place several of them along the length together, And by using a designated periodicity, what can happen is this light from this cavity can be in phase with the light with the next cavity and in phase with the light. So we can couple all of them together and lock them together in a phase lock fashion. The advantage of doing this is the following. When you make the cavity smaller, the radiation from cavity is higher. So now in addition to these slits which don't radiate much, you have light coming out from the edges and from each one of these edges. So we can also collect that kind of light that's coming from the edges. So this is a cartoon kind of demonstration, not actual simulation. You have light coming out from the edges, and if you place them in the right manner, there is actually mode which is hanging on to this top metal layer in vacuum, or you can call it air, or in vacuum where the laser sits, and there's a mode just hanging in air. So this is kind of a unique semiconductor laser which you don't see in any other type of laser. Not where the resonant mode or light or laser, the resonant field is actually also hanging in outside in air, maybe a few hundred micron length on the top. And if you combine them together, and I won't go into the detail of the periodicity, we can do for example, we use COMSOL for our finite element simulations, and when you have a cavity structure, you put it in COMSOL and look at all the resonant modes that exist. The way laser will work is it will excite the lowest loss mode, obviously, and then it will be locked at that mode. So we have to make sure the mode that we want, which will give a good beam, it's in phase, is the lowest loss mode. So that's where the cavity engineering goes. But that's how this mode looks like, the lowest loss. So this is a frequency, all the modes that exist in this cavity, their radiation loss. So we always use per centimeter. So 10 per centimeter is equivalent to about 40 dB per centimeter. So that's how you can, or 1 inverse centimeter is equivalent to 4 dB per centimeter. So that's if for those who think in terms of dB per centimeter. So a typical loss for our mode is 10 per centimeter, and that's how the mode looks like. And when you simulate that, again, I'll skip some of these simulation results. So this is, I will like to show how these structures look like finally. So these small microcavities are mentioned, many of them. They are kind of connected together at the sides because we want to apply current to them or voltage to them. So they have these bonding pads where we put our wire bonds, and those the current that's going from top to bottom is going through all of these. These are the air gaps between those microcavities, and these are the thin slits. And this is all done by conventional lithography. So I was asking Dr. Raghunathan about E-beam. We don't need E-beam lithography for these because we're working at long wavelengths. So the thickness of these slits may be few microns, 3-4 microns. The spacing could be around maybe 30-40 microns. I don't exactly remember. So I think for the periodicity, maybe actually 90 micron for this case. So this is easily done by just conventional lithography. And then this is a typical laser that will look like. So this is a laser with 2 watt output power in pulse mode of operation, about at around 3-4% duty cycle of operation. So that's how people usually plot it. Current versus light. So that's this curve. As you keep on increasing the voltage and higher current, then starts to laze. It's not straight linear because there is something else going on in the transport, but nevertheless, this just shows how the power is, and the maximum power is around 2000 milliwatt. This one is the IV curve that I showed. This is the real IV curve of this laser diode. For those who actually work with lasers, you might not be used to seeing such high voltages. So they do require a lot of voltage, so about 15 to 20 volts, and the currents of around 3 to 4 amps. So this is a fairly You can see if it was to work in DC or CW operation, it would be 20 volts, 3 amps. So that would be 60 watt of, like a 60 watt light bulb. That would be too much. So that's why they don't work in CW anymore. That's one of our goals in the next 2-3 years, 3-4 years. Maybe we can make a CW laser, which means we are not applying pulses, just using a battery, and it's constantly on. So in the last, I guess, couple of minutes, I just want to show some of the other stuff we are doing. We are trying to find different ways of coupling them, find new structures to increase their power even more, and maybe make CW lasers. That's they're really unique devices. You can do some of this stuff that some of the type of cavities we are doing here in other wavelengths. And then we are trying to do, we did some wavelength beam combining, which means what our goal is, we place 10 or 15 or 20 lasers on a chip, which we can have. Each one can be emitting at a slightly different frequency. And then we beam combine all of their are emitting, and we use a lens and a grating to combine all of their beams so that in far field they're all going together in the same direction and overlapped. So that's some of the stuff that, because that's useful when you want to use these lasers for spectroscopy. You want to use a multi-frequency array to probe different frequencies on a material. And we have started on using making some ways to pass this laser light through liquid, so some chemicals. So we made these channels in HDP, which is polyethylene, to make really thin channel. What we need to do, as I said, a 50 micron wide water channel will absorb 90% of light. So we need to make really thin channels. That's how we did. We made very thin channels in HDP. We tried many different things that didn't work. So this is kind of a very thin channel inside, sandwich between two polyethylene layers. And now we can put water in it through inlet and outlet or some other chemical, and when pass light through it through direct absorption spectroscopy. So this is pretty unique. You cannot do with any other type of terahertz source that we have. And we analyze different kinds of fuels as a first way to do it, and lubricants and any other chemicals, and we are able to accurately calculate their dielectric constant at terahertz frequencies, and they can differ. So this can be a way to do some analysis of different chemicals through these channels. So I think I skipped some of the material, and that's where we are going. Our goal is to reach some of this stage. For example, this is a picture of not terahertz QCLs, but midIR QCL array. This is an electronic circuit. This is not the main part. The actual part is this QCL array. So this is a semiconductor chip with perhaps 50 lasers, I think, or some 32 lasers, each emitting at a slightly different frequencies, and they are now solid, and you can bias them through this electronic circuit, and you can have a broadband laser array for spectroscopy. So that's the kind of application we are looking at. There's some microscope with such type of mid-infrared light. So hopefully one day we can also do something like this with terahertz, where there is a lot of application possibility for doing spectroscopy with such laser arrays. But there's a lot of challenges to be met. That's where what we are doing. So I hope that's all I have to say today. I hope you learned something new if you did not know this already. And I'm happy to take some questions. And thanks again for this invitation.
Thank you very much, Sushil, for the very interesting talk. And so are there any questions? You can either raise your hand and unmute yourself and ask, or type in the chat box. Let me start. So when you were talking about the smaller size cavities, right, and then somehow phase locking or shaping the wavefront so that they can coherently combine. So
yes.
In that context, when you're talking about smaller length cavities, would the threshold go up? Is that at all a concern?
Yes, so that's a good question. So on this image, if you make the cavity smaller, just like in a Fabry-Perot cavity, basically a smaller cavity means higher radiation loss or a smaller Q factor, so threshold will go up. But since then we combine multiple cavities together and they phase lock, the mode that's eventually the loss of this phase lock mode is not that high as it would be for a single cavity. So that's where the game has to be played. You do not want the loss to become so high that, so what happens is, and when we are trying, when the loss is so high, it will not be a laser anymore. We bias it, no light comes out. There's no threshold, and so you have to find the sweet spot, and you keep on increasing. So that's where the game to be played in laser development. You keep on increasing this loss, you increase the threshold, but your range of lasing in the current becomes smaller. So there is an optimum spot where you can enhance the maximum power. Yes, right.
Any other questions? You can unmute yourself and ask. Is there interest in using these kind of meta surfaces and all that for wavefront shaping in front of the laser cavity for better emission profile?
Yes, very much so. In fact, that's one of the things we would like to do. Maybe not for that's actually at UCLA itself. The other way of doing beam shaping is through using some sort of meta surface. They actually do something different. They have the meta surface made of the QCL medium itself. This is a picture, and then they use an external mirror, and this becomes like a VEXEL, they call it. So they are able to do this to beam shape emission from these. So there's a different way. Now there are other ways. The beam that's coming out already, you can beam shape it. I think there is not much you can do, and you will lose power if you do. So it turns out, for work done so far, if you can do this in-house, means in the cavity itself, it's much better. The advantage of meta surfaces would be probably in maybe beam steering, if you could do, or some electrical control, or if you could make a meta surface lens, because these HDP material or any type of material that we use for lenses, they're also absorptive. So they can, if you just focus this light with a lens, you will lose 30% or so, or 40% of light. So with meta surface in reflection mode, perhaps you can get much higher efficiency. So I think that's where something can be done.
Okay. Any other questions? Okay, looks like there are no other questions. So if not, we'll thank Sushil once more for the interesting talk, and hopefully we learned something about quantum cascade lasers today. So with that, we will conclude the webinar, and I would like to thank all the audience for attending, and hope to see you in the next webinar in this series. Right? Thank you.
Thank you. Thank you for attending, everyone.
Thank you. So Sushil, I can stick around for a bit, or if you want to discuss later, I'll be